Oh, the answer's 2. And hi, how are you doing? And hey, everybody. I am so pleased that you have again chosen, in vast numbers, the vast majority of you today have chosen to show up for your learning. Come on in, learn the next new thing, and then get ready for the trigonometry test that we have on Monday. The main thing that we're getting ready for, of course, is your future. And we fill your minds with new math knowledge, and that prepares you well. Today's topic is trigonometric identities. So we already are familiar with this idea of identities. Here's an example of some identities. If I have x squared minus 25, would you say that that's identical to this one? Yeah, well, it is. It's a difference of squares. It factors that way. So you'll notice if I take a look at the graphs and toggle that one on and off, they're totally coincident. They're exactly the same thing. Their graphs are the same. Algebraically, they're the same, but they look very different. Okay? The same thing if I have 2 multiplied by 2 to the negative x is actually the same thing as 1/2 raised to the x minus 1. We can use our exponent laws to show that those two things are equivalent. And if we look graphically, they're going to be the same thing as well. Now, if you thought those were fun, the trigonometric fun that we're going to have with looking at trigonometric identities. Okay, recall that sine, cosine, tangent, cotangent, secant, cosecant, these are all just different opposites, adjacents, and hypotenuse, and the ratios of those 3 elements of a triangle. And to prove these identities, the first thing that you're going to want to take down as a note is how to write all of these things as sine, cosine, and sine and cosine. So recall, tangent, we've already seen the meme about tangent. If I want to write tangent as sine and cosine, anyone remember how to do that? You said sine over cos? Yeah, sine over cos. So it's tan theta is equal to sine theta over cosine theta. Let's look at why. So sine theta would be opposite over hypotenuse. That's sine theta. And cosine theta would be adjacent over hypotenuse. We've kind of gotten out of using opposite and adjacent, though. Instead of opposite, I encourage you to think of the y value over the hypotenuse, and the adjacent as the x value over that hypotenuse. Okay? Wherever you want, man. Now, here, simplify this. We're dividing a fraction by a fraction. So we turn that into a multiplication problem by flipping and multiplying the bottom. So here, y over h flips and then the bottom will flip to become h over x. That cancels, and then you get y over x. Well, that's just tangent. So these two things are the same. So that's how you would write tangent as sine over cosine. Let's take a look at the reciprocal trigonometric ratios. If I had cosecant theta, how would I write that as either some combination of sine or cosine? What is cosecant? Who can recall? Who can remember which one that has to do with? So cotangent goes with which one? So we have 3 secondary trigonometric ratios, the reciprocal ones, and cotangent goes with tangent. And that one's pretty easy to remember. So if I have cotangent down here, cotangent theta, well, that's just 1 over tan theta. Or just take tan theta and flip it. So we can write that as sine over cosine. Sorry, we can write that as cosine over sine. Cosine theta over sine theta. Because it's just flipped tangent. So that would be my identity for cotangent. I wouldn't use this one. I would use this one. Cotangent is cosine over sine. Cosecant, which one does cosecant go with? There's cosecant and secant. Cosecant goes with sine, and how do you remember that? Yeah. Each pair has a co, so cosecant has a co, sine doesn't, so we need to add the one that has the co. So cosecant is written as 1 over sine theta. That's an identity we can use. And secant theta, well, by process of elimination, that's 1 over cosine theta. So these are all the different ways you can write the different trigonometric relationships as functions of sine and cosine. Now let's take a look at when we have multiplication and division, and we've been asked to prove statements like this. Okay. In these proofs, we're going to convert everything to sine and cosine, and then use fraction, multiplication, and division to simplify these things. So let's take a look at how that can go. But one important thing, one skill that we're going to develop is split this equation into its left side and its right side and work on each separately. That keeps you from using neat inverse operations to go between the two sides. We want to prove that the left side is the same as the right side by working the left side independently from the right side. So let's take a look at how that looks. First, I say this is the left side of the equation, and this is the right side of the equation. If I work on the right side first, I could say tan x is equal to sine x over cosine x. And there's not much more I can do to simplify that. That's as simplified as I could get the right side. Let's work on the left side. Sine x multiplied by secant x. Well, secant x, I can write that as, secant doesn't have a co, so it's 1 over cosine. So sine x multiplied by 1 over cosine x. Oh, and that would just be equal to, we multiply top times top over bottom times bottom, so that's equal to sine x over cosine x. And then we can say, well, that equals the right side. And then you have this sort of statement, since the left side equals the right side, therefore, and then you can recopy your identity. Therefore, sine x times secant x equals tan x. Agree?
Wait, can you explain why you put cosecant or secant in the bracket?
Why put secant in the bracket?
Yeah.
Oh, just because I wanted to be clear, I'm multiplying sine x by that whole fraction.
Okay.
And then when I multiply top times top, it's sine x times 1 is sine x. And then 1 on the bottom times cos x is just cos x on the bottom. So I just wanted to do that. Adding those brackets doesn't change the bedmas. There's no bedmas that gets altered its order by doing that, so it's fine to add those brackets. Okay, next one. Let's prove that tan x multiplied by cosine x divided by sine x is equal to 1. Okay, so here my left side has lots of funky stuff. My right side, there's nothing I need to do to simplify that. So let's leave the right side alone and work exclusively on the left side. So here I might say left side, okay, tan x, cosine x, sine x. So tan x, I'm going to write that as sine x over cosine x. That's tangent of x. And then that's going to multiply here cosine of x. And I guess, Acredi, the answer is I prefer to show multiplication with brackets rather than just the way they do, because that looks like a weird sentence, right? You kind of need to be able to see when they write it that way that we have some brackets around there. And I tend to use theta as opposed to x, like this handout is using x. I will use theta. And it's a little easier to see. But that's tan x multiplied by cosine x. So I wrote tan x as a new way, sine x over cosine x, multiplied by cosine x divided by sine x. Okay? And now we can see if I'm multiplying sine x over cosine x by cosine x, well, we can do some canceling here. Just like when you're multiplying fractions, you can always cancel factors that appear on the top and the bottom that are the same. We got a real workout with that with equivalent rational polynomial expressions in Unit 2. And here we get to cancel as well. Here cosine x will cancel cosine x. Because if I multiply by cosine x and then divide by cosine x, that's just multiplying by 1. So that will cancel away. And then we would have sine x divided by sine x. Sine x divided by sine x. Those both cancel, and that equals 1, and that equals the right side. So therefore, tan x multiplied by cosine x, all divided by sine x, will equal 1. One more example of these multiplication ones. Cosecant x divided by cotangent x equals secant of x. Okay, let's try. So here the right side and the left side both need some work to be expressed as functions of sine and cosine. So let's go through that. Cosecant x, that is a co in it. So we're going to use 1 over sine. So we can write that out. So here is the working on the left side. Cosecant x is 1 over sine x divided by cotangent of x. Well, cotangent of x was cosine of x divided by sine over x. Okay, so that's what the left side is equal to in terms of sine and cosine. Let's flip that bottom fraction and multiply. So then we're going to have this is equal to 1 over sine x, the numerator, multiplied by the reciprocal of the denominator. I flip the denominator to be sine x over cosine x. And then we see this cancels. We have the same factor on the top and the bottom, so those cancel away, leaving us with 1 over cosine x. Let's work on the right side. Secant of x is equal to 1 over cosine x. That was easy. That equals the left side. So be aware that we're not working on both sides simultaneously and getting some statement like 1 equals 1 at the end. You work the left side independently of the right side, show that they are equal, massage them both as like functions of sine and cosine into the same thing. Once they're the same thing, you triumphantly say, therefore, cosecant x, CSC x divided by cotangent of x is just a fancy way of saying the secant of x. Cool. All right. These are identities that use multiplication and division. We're also going to see identities that use the addition and subtraction of fractions. So here, when you're multiplying and dividing fractions, you do not need a common denominator. This can't be overstated enough. If you're adding and subtracting fractions, you always need a common denominator. So let's go for it. When we're doing these, we're going to have to do things like multiply the top and the bottom by the opposite thing in order to the example they give down here is a good one. Let me go through this one and show you how we would work that. So here, let's work the left side. So the left side here, secant x plus sine x. Okay, let's go. So secant x, I can write that as 1 over cosine of x. And then I'm going to be adding sine x. So I'll put sine x up here. But I don't have the proper common denominator. So what I'm going to do is get out my create a common denominator pen. And I'm going to multiply that top and bottom by this denominator here. Cosine of x over cosine of x. And I recall that sine x is just sine x over 1. Everything is something over 1. So now I have a common denominator, cosine of x. And now I can add 1 plus the tops multiply here, sine x times cosine x. All divided by the common denominator. 1 times cosine of x is cosine of x. Notice they have the same common denominator, so I just write that here, cosine of x. Oh, well, that equals the right side. Okay, so the left side, once we converted that to sine and cosine, and then created our common denominator, we found that equaled the right side. So since the left side equals the right side, therefore, and then we can just copy down our identity. Secant x plus sine x is equal to 1 plus sine x multiplied by cosine x divided by cosine x. Oscar.
So why can't we like work on both sides at the same time? Because I kind of
You might divide by 0 and then prove that anything equals anything else. Have you seen that famous math meme where 1 equals 2? And the math teacher will prove that because A is like been given as 1 and B has been given as 2, and then at some point he divides by B minus 2A. And you don't notice that B minus 2A is 0, and then you can make anything equal anything. And then A equals B and 1 equals 2, and all of math crumbles. So we prevent those types of tomfoolery by working on the different sides separately.
Okay.
Oh, I didn't erase that one very effectively. Let's go through that one. So next, we're going to do this equality here. There's solutions under there that I've covered up because I want the practice. All right, let's try this one. So cotangent of x plus secant x. Let's work on that side first. So the left side here, cotangent of x. We recall that tangent is sine x over cosine x. Cotangent is just flipped that. So this is cosine x over sine x. Oops, and I proceed to write down the other thing. Cosine of x divided by sine of x is cotangent x. And I'm going to add that to secant x. So that's 1 over cosine. I've got two different things on my denominators there. Oh dear, how will I deal with that? Well, if I multiply this one, top and bottom, by cosine of x, that will create sine x cos x as the denominator over there. And if I multiply this one, top and bottom, by sine x, then that will also create a common denominator. If you recall the metaphor of the jealous toddlers, the toddler notices the other toddler has a toy that it doesn't have. It needs that toy as well. So this fraction had a sine x toy in the denominator. So this one needs to be given that so that it feels that the world is fair. And this one has a cosine x, so the other one needs to be given that toy. Malcolm?
So like, can you multiply any side by anything you want?
I can multiply top and bottom by the same thing, anything I want.
Okay.
But I do so strategically so I can create a common denominator.
So you're not like, you're trying to solve it to make it the same.
Yeah, I want to.
That it's the same.
Yeah, I want to prove that it's the same by algebraically manipulating it so that we get the same thing on the other side.
Okay.
Yeah. So let's go. Then we have to, let's take another line to simplify those fractions. Cosine x multiplied by cosine x is written this way. Cosine squared of x. That means cosine times cosine. And that's where we'll put the square. It's not cosine x squared, because that would mean take x, square it, and then take the cosine of the result. We don't want to do that. We want to take the cosine of x and then square the result of that. Cosine multiplied by cosine. And this is the way it's written. Okay? So just, I'm going to erase this. Don't copy this down. It's not the same thing as saying cosine x squared. It's not the same. That's x squared and then take the cosine. Don't write that. Okay. Oh, shoot. Oh, man. What am I going to do? No, it doesn't work. There's no undo button to copy it. All right, so here, cotangent x plus secant x. They wrote that as cotangent x plus 1 over cosine of x. Another line to get to where I was here, which is writing cotangent of x as cosine x over sine x. Then they create the common denominator here. Same thing we were doing. And then multiplying that through. Be very noticing that we write cosine times cosine as cosine squared of x, not cosine x squared. It's different. And then 1 times sine x is just sine x. And then you have cosine squared x plus sine x, all divided by sine x cos x. Go ahead and check that out. It's the same as that. So just add your fractions. All right, so I'll give you a second to copy that one. And then there's one more category of identities to look at before I release you to practice the ones on the last page. Oh, and this set of handouts has a lot to practice. I'll put it on the D2L. It's like 20 pages, lots more practice, some special cases and other things like that if you want to go to a high level with this skill. It's certainly something that shows up again in advanced functions, and you'll learn more of these identities in advanced functions. So you want to be solid on these before you go into that course. And Delta Math doesn't really have any good practice for this, so you got to practice with these handouts. All right, ready to go? Let's go. One more type of identity that we're going to take a look at. Oh, yes. So here we go. These ones use what are called the three special identities. And if you have this one here is worth taking a look at. Sine squared x plus cosine squared x equals 1. And from that, and just converting to different like sines and cosines, we can get these other ones as well. And they can be rearranged as well. So like if sine squared x plus cosine squared x equals 1, I could subtract sine squared x from both sides to say that cosine squared x is equal to 1 minus sine squared x, or sine squared x is 1 minus cosine squared x. They're very simple rearrangements of both sides. If I really rearrange them, I can get these ones. So you want to recognize this when you see it and know that sine squared x plus cosine squared x equals 1, and that it can be rearranged in different ways. All right, let's take a look at y. Let's take a brief look at y. Okay, sine squared x plus cosine squared x. And let's call that the left side of this, and our right side is equal to 1. Let's see if we can prove that. We can't make any progress by writing it as sine and cosine. It's already written as sine and cosine. So let's write it as x over hypotenuse for cosine and y over hypotenuse for cosine. And we'll draw a little triangle here to help us understand why that might be true. Recall these are right angle triangles, and you probably see it right away. Here is my y, here is my x, here is my hypotenuse. Okay, sine squared x is y over hypotenuse, but then we square it because it's sine squared. Cosine squared x is x divided by hypotenuse, but is squared. Okay, and now let's go forward one more line. We will have common denominator. We'll have y squared over hypotenuse squared plus x squared over hypotenuse squared. And then that's just going to be y squared plus x squared divided by hypotenuse squared. But over here, we already knew that y squared plus x squared is equal to h squared because of Pythagorean theorem. So this one's called the Pythagorean identity. Sine squared plus cosine squared equals 1. So let's see. The last thing we can do here is use this formula, substitute it there for y squared plus x squared. And so you have hypotenuse squared divided by hypotenuse squared, which is equal to 1. All right? So let's go use it. Let's go use it to prove some trig identities. How about? Oh, and these ones here, I'll leave these as challenge problems for you to prove yourself. So you can play with these and see if you can prove that these ones are also true. But we're going to use all of these different identities. Okay, 1 minus cosine squared times tan squared x equals cosine squared of x. Okay, so how are we going to deal with that? Let's start with the left side. Zoom in. Going to need some space for this one. We started the lesson a little later. That's why it's a little later. Still going to get practice time today. Oh, and people have been saying, we need practice time. We need review days. So that's what tomorrow and Friday are for. All right, so let's go. Okay, 1 minus, cosine squared times, cosine squared x times tangent squared x. Let's write tangent as sine x over cosine x. But it's tangent squared. So we have to make sure we still square that. Okay? 1 minus cosine squared x multiplied by sine squared x over cosine squared x. Okay, and then we get out our cancellation pen, which we're always excited to get, and we notice that this multiplication has a cosine squared x multiplying a cosine squared x that's dividing, so those two cancel out. So we have on this side of the equation 1 minus sine squared x. Notice that 1 minus sine squared x is a rearrangement of the Pythagorean identity. 1 minus sine squared x is over here, so it just equals cosine squared x. Equals cosine squared x equals the right side. Here was our right side here. Since left side equals right side, therefore 1 minus cosine squared x multiplied by tan squared x equals cosine squared x. Cool. One more. Oh, yeah, I should give you time to copy that if you need. Questions about this? Malcolm?
You have to write out like the alt like cos 1 minus cos squared x and x, or can you literally just write that for
Therefore, left side equals right side. Mrs. Hall, if someone gets to here and they've triumphantly proven that the right side is equal to the left side, do you have them say therefore the whole equation, or do you just say therefore left side equals right side?
Honest answer, left side equals right side.
Okay, cool. We'll go with that.
I'm lazy. It's faster.
Yeah, cool.
Do you happen to have a plug for
The computer?
that? Yeah,
Yeah, sure. I can spare this one.
you can spare that.
Yeah.
I forgot mine at home.
Sure. I think a Chromebook one works too. There you are.
Oh, it does.
Yeah.
Maybe
no,
it
maybe it
doesn't.
doesn't.
No, I don't think so. I think they're bigger than this.
And thank you for your participation in our lesson, Ms. Hall.
Anytime.
One last example.
In here. Hi, everybody. Tell people I've taught. Yay. Bye.
Okay, let's go. Isn't she a delight? All right. Yeah, only if only you could upgrade, right? So, okay, let's go. Sine x minus cosecant x. Let's use that. So let's start with the left side. Here, sine x can't be written in any other way. It's just sine x. Well, it can be, but not really. Minus cosecant x. So we're going to subtract 1 over sine x. That's cosecant of x. Now we need to create that common denominator. So I'm already wishing I had given myself a little bit more space. Oh, no, I did it again. Forgot, I can't use erasing because it erases my erasing of their work. You want to see me work through it or just talk through their solution? Talk through their solution. Let's go. Sine x minus 1 over sine x. And then they take a whole nother line to create their common denominator. Look at them go. So conscientious. Okay. Then that would create sine squared x over sine x when these two multiply together. Sine squared x is how that's read. It's not sine x squared. That is different. I'll show you in Desmos in a second. They're very different. And then minus 1 over sine x. So when we then, wow, they really take their time here. And then they create that common denominator and then express it as sine squared x minus 1. And they notice that sine squared x minus 1, they're going to use a special identity here. They notice that if you have 1 equals sine squared x plus cosine squared x, you can create, by subtracting 1 from both sides and subtracting cosine squared x from both sides, cos squared x, that you will get 1 minus 1 cancels away. You get minus cosine squared x is equal to sine squared x minus 1. That's just a rearrangement of the Pythagorean identity. They use that to substitute for the numerator. So you get negative cosine squared x over sine x. And then write that out as 2 multiplications of cosine. cosine x times cosine x, and then they notice that cosine x divided by sine x is cotangent of x. So they've worked that out. So they spread out the two cosine multiplications so that they can form cotangent of x. Okay, I wouldn't do it that way. There's a different way to do it, and I'll show you my way over here. This is fine. This is great, actually. Of course, it's great. It's correct. But I'll show you what I do. I would work my left side to this point, actually this point here, and leave it. That's where I would leave my left side. And then I work the right side to match that. And I'll show you. So here the right side is a negative cotangent x multiplied by cosine of x. So let's write that over here in a different color. We'll use forest green. It was negative cotangent of x multiplied by cosine of x. Is that right? Yeah. Negative cotangent x cosine x. So remember, I don't have this in my solution, okay? I am going to stop here and work this side. Here I say right side over here. And then I express cotangent of x as negative cosine x over sine x multiplied by cosine of x. Multiply your cosines gives you negative cosine squared x divided by sine x. And we've already shown that the left side equals that right there. So that's just a different way. And it shows that your neighbor might have a different way of proving something is true than you do. And that's okay too with these ones. So on the next page, there are several examples that you can practice on your own using these various identities and tricks and tips. And think of them as little brain-teasing puzzles designed to test your fractional, algebraic, and trigonometric manipulation skills. Oh, and I promised that I would show you that sine squared x is not the same thing as sine x squared in Desmos. Let's take a look at what both of them will look like. This will be a nice warm-up for the next unit. This is sine of x. 6 of x, sine x. Looks like that, okay? If I square x, and this is like next unit. We get used to seeing this, and we're going to graph that lots of different ways. Okay, sine x squared, if I square x, it starts to look like that. Ooh, that's a weird one. Okay, sine squared x, on the other hand, looks much tamer, doesn't it? So that's a sine x multiplied by a sine x. Notice that a square is always positive. So this only has positive values, like its domain and range is from 0 to 1 instead of negative 1 to 1. All those negative ones are getting squared up to positive numbers. If I compare that to sine of x, you'll see that they kind of overlap in that interesting way, that way. So all those negative numbers getting squared to positive numbers. Okay, so now go ahead and practice. And any questions, hit me up by email or bring me over your tables. And thank you for showing up for your learning.